Hey everyone! So in this explainer, we're going to do something a little different. Not only are we diving into a really cool topic, Neuro Symbolic AI, we're also going to learn how to read a scientific paper, from the inside out. We're going to use the paper's own structure to figure out how AI is actually learning to reason. So let's get into it. Here's our roadmap for today. And what's cool is this basically mirrors the logical flow of the research paper we're looking at. We'll start with the why, the big problem. Then we'll define our terms so we're all on the same page. After that, we'll walk through the actual solutions they propose, and we'll wrap up by looking at what's next. See? A good paper always lays out the path for you. All right, so every good scientific paper kicks off with an introduction, and its main job is to hook you. It defines a really important problem and makes it clear why we absolutely need to solve it. So what's the big problem we're talking about here? I mean, we've all seen this, right? You can ask one of these super powerful AIs a pretty basic math question or a logic puzzle, and it comes back with an answer that is just confidently wrong. And this isn't just some funny little quirk. It actually points to a really fundamental weakness in how these models are designed. And this quote from the paper, man, it just hits the nail on the head. Large language models, LLMs, they're incredible mimics. They're so good at seeing patterns in all the data they're trained on. But, and this is what the researchers are saying, they don't really get the logic behind it all. They're just copying the steps they've seen before. So the huge question is, how do we get them to make that jump from just mimicking to actually truly reasoning? Okay, so before a paper can really build up its big argument, it has to lay some groundwork. This is usually the definitions section, where they spell out all the key terms. You gotta do this so that everyone, is working from the same playbook. First things first. What do we even mean when we say reasoning? Well, the paper defines it pretty formally as this recursive process. But think of it like building with Legos. Each brick, which is like a step in your logic, has to be placed perfectly on top of the one before it. You have to do that to build something stable, which is, your final answer. And this, right here, this is the proposed solution, Neuro Symbolic AI, or NESI for short. It's a hybrid. The whole idea is to get the best of both worlds. You take the incredible learning and pattern matching skills of neural networks, that's the neuro part, and you combine it with the super strict, rule-based logic of old-school symbolic AI. Now, this is where it gets really interesting, because the paper makes this great connection to how we think. It's an analogy to something called dual process theory. So neural networks are like our system one thinking, fast, intuitive, gut-feeling stuff. And symbolic AI? That's our system two. It's slow, careful, and totally logical. The goal of neurosymbolic AI is to build a machine that can do both. Okay, so we've got the problem, we've got our definitions. Now we're getting to the main event. This is the heart of the paper, the methods section. This is where the authors really show their work and present their big idea, a breakdown of 3 different ways to combine these neural and symbolic systems. So the paper breaks it down into 3 main strategies, and they get more and more integrated as we go. First up, you have the symbolic system acting as a teacher for the LLM. The second way is to have the LLM learn how to use the symbolic system as a kind of tool. And the third, well, that's a true partnership, where they work together from the very beginning. Let's take a closer look at each one. So, approach number 1, symbolic to LLM. Here, the symbolic engine, which is designed for perfect step-by-step logic, is the teacher. It basically creates these flawless reasoning examples like perfect mathematical proofs. We then take all that beautiful structured data and use it to train the LLM. It's kind of like giving a student a math workbook where all the answers and the steps to get there are already perfectly filled out. So why is this such a big deal? Well, it solves a huge problem the paper calls reasoning data scarcity. It's just incredibly difficult and expensive for people to create massive data sets of perfect reasoning. This method just automates the whole thing, creating a nearly endless supply of A+ training material. All right, now for the second approach, LLM to symbolic. We're flipping the roles here. In this setup, the LLM is like a smart project manager. When it hits a problem that it knows it's bad at, like some tricky math or a tough logic puzzle, it doesn't just guess. Instead, it learns to hand off that specific task to an external, specialized symbolic tool that can absolutely crush it. And this is basically how that pipeline works. First, the LLM figures out what needs to be done. It plans the steps. Then it picks the right tool for the job, maybe a calculator, a logic solver, you name it. It calls that tool with the right information, and then, once it gets the result back, it puts it all together into a nice, easy-to-read answer. So the really clever thing here is that this approach fixes what the paper calls reasoning function error. Basically, instead of trying to rely on the LLM's own, sometimes shaky logic, you just swap it out for a tool you know is 100% correct. It's like giving a calculator to a brilliant writer who just happens to be bad at math. And finally, that brings us to the third and, honestly, the most ambitious approach, LLM plus symbolic. This is not about teaching or just using tools anymore. This is about creating one single, deeply blended system. Here, the neural parts and the symbolic parts are built to work hand in hand from start to finish, and they're both optimized together for whatever task they're doing. Yeah, a lot of researchers would call this the holy grail of the field. The dream is to have one unified AI that has the fluid, data-driven learning of a neural network, but also the strict, provable logic of a symbolic system, all baked into one package. This is really where the most exciting stuff is happening right now. You know, no good research paper just ends. It always has a conclusion or future work section. This is where the scientists are honest about what they haven't figured out yet and point to where the research needs to go next. It's a good reminder that science is always an ongoing conversation. So, the paper points out 3 big challenges ahead. First, getting these systems to reason about more than just text. We're talking images, audio, all kinds of data. Second, designing even better, more seamless ways to blend these two systems. And third, and this might be the most important, is getting a real deep understanding of why these hybrid systems work so well, not just the fact that they work. And all of that leaves us with this one final, really critical question. As these AI systems get woven more and more into our daily lives, the difference between an AI that's just a really good mimic and one that we can actually trust to reason logically and reliably, well, that difference isn't just important, it's everything. And that's the challenge that all this research is trying to solve.